here is a summary of the VSEPR theory. Okay, it gave you, now this region of electron density here is, there's so many different ways to call it. It's also called electron clouds. Okay, and well, you see it right here. Okay, and now this showed you that when you have different amount of things, of electron clouds, what if I have only 2 electron clouds? What if I have 3 electron clouds? What if those 3 electron clouds are 3 bonds or 2 bonds, 1 lone pair, so on and so forth. Each of them, you can see, if they have the same amount of electron clouds surrounding them, okay, regardless of you have bonds or lone pairs, your geometry is going to be the same. But with you changing the bond and lone pairs, you can see that your shape of the molecule start to vary. Now, this VSEPR summary sheet, okay, I will put it on eCampus for you to download, print, and review, and we will further talk about these, especially the later ones on the chart, okay, what kind of shape it is, and so on and so forth. And if you want to look at better pictures than the ones that I draw, I would suggest go to your PDF textbook that with the link on your syllabus, and you can probably see much better pictures of different molecules, different shape, than the ones I draw. That's it for today, and I'll see you on the next lecture. Okay, so we were discussing Lewis structure, and we were on the topic of using formal charge to determine between a few possible Lewis structures for the same compound, which one makes better sense. Okay, so here's another example about that. Dinitrogen monoxide, N2O, okay, has 3 possible Lewis structures. Okay, and now what are the 3 possible Lewis structures? There's nitrogen as the central atom, oxygen and the other nitrogen as non-central atoms, and the first one is like that. Altogether you have 5 times 2 plus 6, so 16 electrons, which means 8 pairs. Okay, so 1 triple bond, 1 single bond, or 1 triple bond between nitrogen and 1 single bond between nitrogen and oxygen, and then double bonds between nitrogen, and nitrogen, oxygen. Okay, so using formal charge, determine which one makes better sense. All right, so let's go. First of all, let's find formal charge. Okay. Okay, so nitrogen 1, nitrogen 2, and oxygen. Okay, so for nitrogen 1 in the first structure, so 1, 2, and 3. Okay, nitrogen 1 in the first Lewis structure, remember formal charge equal to the number of valence electron in neutral element minus 1/2 of bonding electron. This guy has 1 pair of electron, 2 bonding electron, and minus the total of non-bonding electron, and this nitrogen here has 6 non-bonding electron, and that's a total of 5 minus 1 minus 6, 5 minus 7, negative 2. The second nitrogen would have 5 minus 1 half. This guy has all bonding electrons, okay, no non-bonding electrons, so a total of octet of 8 non-bonding electrons and 8 bonding electrons and 0 non-bonding electrons. So 5 minus 2 minus 4 plus 1. And the oxygen that you have is 6 valence electrons minus 1/2 times triple bond. So 6 bonding electrons, and 1 pair of electrons belong to oxygen, 1 lone pair, and that's 2 non-bonding electrons. So 6 minus 3 minus 2, so also plus 1. All right, so that's in the first Lewis structure. Now, second Lewis structure, now, the first nitrogen has 5 minus 1/2 of 6 bonding electrons, triple bond. Okay, so 1/2 times 6, and then minus 1 lone pair, so 2 non-bonding electrons. That makes it equal to 0. 5 minus 3 minus 2. The second nitrogen has 5 minus 1/2 times, again, same situation for the central nitrogen. 4 pairs of bonding electrons makes the octet no non-bonding electrons. So 1/2 of the 8 bonding electrons minus 0, and that's plus 1. Okay, and then for the oxygen, 6 minus 1/2 times only 1 pair of bonding electrons, and then 6 non-bonding electrons, negative 1. Okay, all right, and then the third structure, you would have 5 minus 1/2 of a double bond between nitrogen, so 4 bonding electrons, and the first nitrogen would have 2 lone pairs, that's 4 non-bonding electrons, so 5 minus 2 minus 4, negative 1. The second nitrogen, same deal, 5 minus 1/2 times 8 minus 0 plus 1. And then the oxygen, 6 minus 1/2 times double bond, that's 4 bonding electrons minus 2 lone pairs, 4 non-bonding electrons. So that's a total of 0. Okay, so once you figure out the formal charge of each atom in these 3 structures, now let's apply the rules and let's refresh our memory. The 2 rules regarding formal charge is, number 1 is make formal charge as close to 0 as possible. Okay, now everybody want to be stable, everybody don't want to, okay, have positive or negative formal charges, because positive formal charges means you are losing. You're essentially losing electrons. Now, negative formal charges means that you're essentially gaining electrons. And gain or lose, now, covalent is all about sharing. Okay, so if they don't have to lose or gain, they don't want to. Okay, we want everybody to be happy in a covalent structure here. So make formal charge as close to 0 as possible. And using that rule, comparing the 3 structures, so there is one that we can eliminate actually. Look at this one. Everybody has formal charge. Okay, and you have a formal charge negative 2 there as well. And for the structures 2 and 3, okay, you have 1 atoms carrying 0, and you have the other 2 are only plus 1, negative 1. So with this, we're eliminating the first structure. Okay, but between the second and third structure, we don't really have a clear winner here because it's 0 plus 1, negative 1, okay, for both of the 2 Lewis structures. And this is where your rule number 2, should kick in, okay? And rule number 2 goes as we prefer the negative formal charge on the more electronegative species. Okay, so we have the negative here, we have the negative here. Okay, now we prefer the formal charge to be as close to 0 as possible, but if we have to have negative formal charge, then we want this to be on the more electronegative element. Okay, now looking at oxygen and nitrogen. Okay, if you have a periodic table, you look at it, okay, the trend of electronegativity is going left to right, increase, and that one right there, oxygen is directly on the right of nitrogen. Okay, so oxygen has higher electronegativity. Okay, so -1 formal charge should be on oxygen. Okay, structure number 2 has the -1 charge, formal charge on oxygen, and structure number 3 has negative formal charge on nitrogen. Okay, so structure number 3 eliminated, and structure number 2 is what we're looking for. Okay, so use the rules of formal charges. Now, with molecules or polyatomic ions having equivalent structures, then you would have a way to actually figure out which lowest structure makes better sense. And of course, if you're looking at the structure of N2O here, you would think, well, you told us about we draw lowest structure of carbon dioxide before. Okay, it's the same situation: 1 central atom, 2 non-central atom, and a total of 16 electrons, 8 pairs to use. Why over there in carbon dioxide, you told us it's this, and you didn't even bother with, putting triple bond and single bond, and switching side on this. The reason of that is, well, you do in carbon dioxide, the 2 non-central atoms are completely equivalent to each other. They're both oxygen. Okay, there's no reason that the 2 of them behave differently when they are the exact same atom and they're making the exact same bonds. All right, now if you look at N2O, your 2 non-central atoms are different. And when those non-central atoms are different, then you don't know, okay, that they would behave the same way. And actually our result here showed us that they don't behave the same. Okay, so if you calculate formal charge of carbon dioxide, the current, this lowest structure, and you can make this, triple bond, single bond on each side, and calculate the formal charge, and I guarantee you our rules would say that this is the more stable structure anyway. Okay, so nothing against the rules here. All right, so this here completes our talk about lowest structure. So at this point, you have a detailed procedure of drawing lowest structure for a given molecule, counting the electrons, and going through the skeletal structure, so on and so forth. Okay, and along the way, we talked about a few different situations regarding formal charge, regarding lowest structure, such as expanded octet, such as resonance structure, and such as using formal charge to differentiate the different lowest structures for the same compound. Okay, now, like I said previously in the email, okay, Lewis structure is such an important part of the the rest of the Chem 115 contents that you have to practice on it to make sure you know the steps of drawing it and make sure you can draw it quickly and correctly, okay? Because a lot of the future topics in Chem 115 are depending on your ability to draw a good Lewis structure for your compound, okay? And now the next thing we're going to be discussing here is called the shape of molecules. All right, so we have drawn Lewis structure, okay? And when we draw Lewis structure, we have, okay, central atoms, non-central atoms, okay? And really, you can draw it however you want, okay? As long as you're showing the electrons, as long as you're showing the electron pairs, as long as you get your bonds correct, okay, you can draw it however you want, okay? But each of these molecules, okay, that you draw, you know Lewis structure, okay? Remember, when you draw Lewis structure, you draw it on a surface, okay? Whether it's, for me, it's on a screen, and for you, it could be on a piece of paper, okay? But a screen or a piece of paper is two-dimensional, okay? Now, your molecules are not two-dimensional. Your molecules exist in the world that we're living in, and the world we're living in is a 3D world, okay? So, shape of molecule, okay, is dealing with 3D situations. And now, what do we do to determine the shape of molecule? Okay, now, to be able to do shape of molecule, we're really focusing on two things. Number one, what is the Lewis structure of your given molecule? Okay, because that gave us the information of how many bonds, what kind of bonds are made in your molecule, and that is actually one of the determining factor in how do your molecule extend itself in a 3D world, okay? Now, and the other thing that we're relying on, okay, is called the VSEPR theory. Okay, so what's this? This is the valence shell electron pair repulsion theory. Now, what is this theory all about? It's about one thing, okay? Now, all of these electron pairs that we have in Lewis structure, okay, are coming from valence shell of different atoms within your molecule, okay? Because that calculation we did earlier is all about valence electron, and we can only use valence electron to build our Lewis structure, okay? So, and now, one thing we do know is that all of these valence shell electron pairs, all of these little dashes that we have in our Lewis structure, okay, they all have negative charge. Duh, they're electrons. Okay, and because they all have negative charge, they hate each other. They're trying their best to push each other away. Okay, now, so the way that we determine the shape of molecules, is depending on, well, how these electron pairs, and we're not looking at any of the non-central atoms. In the shape of molecule, those guys are not as important. Okay, now, who's important? All the electron pairs on your central atom. Okay, these guys push each other away and as far as possible, and they are going to determine. Okay, so essentially valence shell electron pair on central atom will repulse each other and eventually resulted in different shape of molecules. Okay, so now let's see some examples. Okay, so first, let's see beryllium chloride. Okay, you look at this, you go, isn't beryllium a metal and chlorine a non-metal, and shouldn't this be an ionic compound? Okay, well, it's beryllium chloride, like magnesium chloride, calcium chloride will be ionic compounds. Okay, now beryllium chloride is actually not a ionic compound. Well, if you go back to the part that we discussed, electronegativity, you know that you have to have electronegativity difference between the two atoms higher than 2.0 to get a ionic bond. And beryllium and chlorine's electronegativity will just happen to be much closer, and their difference is actually smaller than 2.0. And that makes beryllium chloride a molecular compound. Okay, so, beryllium is in group 2, chlorine is in group 7, 2 of them, total of 16 electrons, 8 pairs. You draw the Lewis structure, beryllium, 2 chlorine, 1 pair for each. Okay, so looks like I'm gonna have to do double bond, but then, wait for a second. Think about the exceptions, okay, to octet that we talk about in Lewis structure part. Beryllium needs only 4 electrons. Well, it already got 4. That's perfect. Chlorine has octet. All right. So now think about this particular molecule. Okay. What kind of shape it should take? On your central, like I said, focus on just the electron pairs on the central atom. Okay, this is 1, this is 2, and beryllium only have those 2 pairs. Now, let me remind you, electron pairs have negative charges, and they hate each other. And beryllium have only 2 on them, so these 2 are gonna try to stay as far away from each other as possible. And how do you stay as far away from each other as possible? If that electron pair is on the other side of the beryllium nucleus, I'm going to stay on this side of the nucleus. I don't even want to see him. Okay, that's how much I hate him. And for the electrons. And now, if for the 2 electron pairs to stay as far away as possible, they are 180 degree apart. Direct opposite sides of beryllium. Well, if this molecule, Okay, the two central atoms, the two electron pairs on the central atom is taking a 180-degree angle against each other. Then we say this molecule has a linear geometry, and the molecule has linear shape. Okay, so beryllium chloride is a linear molecule. Okay, now why do you repeat yourself saying linear geometry and linear shape? Well, because these two are actually two different things, and it's going to show up on different, more complicated molecules. You're going to see their difference. Okay. Now, all right. So now let's take a look at boron trifluoride. Boron is in group 3. You have fluorine has 7, 3 fluorine. That's a total of 24 electrons. 12 pair. Okay, and very easily you can draw the Lewis structure of beryllium trifluoride. So, and again, boron needs only 6 electrons. Boron is another exception we talked about. Okay, so now, again, for the shape, we're looking at the central atom and what's surrounding the central atom. Okay, and there are 3 bonds surrounding the central atom. And these 3 bonds hate each other. They're going to try to stay away from each other as far as possible. Okay, and how do you stay for 3 things? So this is 180 degree. For 3 things, how do they stay as far away as possible? This is how. All 3 of them are equivalent. 120 degree apart, 120 degree apart, 120 degree apart. This is as far away as you can do with 3 electron pairs staying from each other. Now, and in this case, we say the beryllium trifluoride has trigonal planar geometry and trigonal planar shape. Okay, and you see me going again with the idea of geometry and idea of a shape. And for both of the 2 molecules in the example we had so far, you can see that their shape and their geometry, we're using the same description on them. Okay, are there any atoms or molecules or polyatomic ions, okay, that actually have different description on geometry and shape? Well, let's see. What if I have polyatomic ion of Bf2 negative? So this is a 3 plus 7 times 2 plus 1 because of the negative charge. That's a total of 18 electrons, 9 pairs. So if you draw the Lewis structure, you would have boron, fluorine, fluorine. Both fluorine have octet. That's 8 pairs of electron you use. You have 9 pairs, so you have 1 pair left, and any leftover electron we put on the central atom. So there you go. And let's change that. Okay, So this is the Lewis structure, and of course we put a bracket on and show the negative charge. This is the Lewis structure for Bf2 negative. Now, what kind of geometry and shape this guy have? Well, you still have 3 pairs of electrons surrounding the central atom. Okay, that should be obvious to everybody. And of course, you would think that, okay, shouldn't they still stay 120 degree apart from each other? This, because we only care about electrons, right? No. And yes, and that means that your Bf2 negative polyatomic ion, okay, would have the same kind of layout with Bf3. And that same kind of layout, we're going to call it trigonal planar geometry. Okay, and the geometry, we care about just how the electrons extended out from your central atom. We don't care about anything else. But now, for the shape of molecule, okay, are you going to call this trigonal planar? I don't think so. What do you mean? Well, think about this electron pair. Right now, we're using a dash to represent electrons. But you got to remember, electrons are extremely small and moves extremely fast. Okay? What does that mean? That means if you're looking, let's say today we're using our technology, we're looking directly at one single polyatomic ion of Bf2 negative. And when you look at it, do you see electrons? Do you really see that dash extended out from the boron nucleus? No. You're not going to see anything. So this is actually what you see. You're going to see a nucleus, that's boron, and then you're going to see 2 nucleus, okay? So that's your boron, that's your fluorine, that's your fluorine. And these 2 would be (120 degree apart). But outside of this, do you see electrons around this area? No. You know it's there, okay? That lone pair on your boron is real. There is 1 pair of electrons that belongs to boron only, wasn't shared between boron and another element. But now, if this is what you can see, does that look the same shape-wise with Bf3? Bf3 look like this. And it's a symmetrical structure. Okay, 3 different symmetry axes. And what about this guy? Do you have 3 different symmetry axis? No. Okay, and this is why we say Bf2 negative, it has a trigonal planar geometry because geometry cares only about these electron pairs. Okay, but it would have what we call here a bent shape. Okay, 3 atoms, 3 nucleus could make a linear shape like beryllium chloride that we discussed earlier, but in this case, because you have 1 pair of electron actually took one of the 3 positions off the trigonal planar. Now, shape-wise, when you look at the nucleus, when you look at the 3 atoms that you have, it's like a straight line being bended. That's what why we call it a bent shape. Okay, so does that mean that however many electron pairs you have surrounding the central atom would determine totally the geometry and the shape of molecules? Not necessarily. Okay, so let's beryllium. That's two bonds, two single bonds, two double bonds. Both are two electron clouds. Okay, because no matter how much your electron pairs hate each other, the electrons within the same bond, okay, they're not going to be able to push each other far away. Because, I mean, they exist between the two nucleus. Where else do you want it to go? To the other side of the atom? Of the central atom? It's not going to happen. Okay, look at our next example. Let's go for carbon dioxide. Okay, we already drew the Lewis structure before quite a few times for this guy. So I'm not going to bother calculating and whatever. Okay, so here's the Lewis structure. Now, okay, so this have two pairs of electrons, two double bonds. Okay, each bond is two pairs of electrons. So when I'm looking at this, should I count this as two bonds, two things, two electron clouds, however you want to call it, extended out of the central atom carbon's nucleus? Or do I view this as four different things, okay, coming out? Okay, and let's make it very clear. So when we are counting electron clouds surrounding central atom, each bond, and this is regardless of whether it's single, double, or triple. Okay, each bond, okay, is counted as one electron cloud. Okay, and each lone pair. Remember, we put some leftover electrons on some of the central atoms after I dealt with all the non-central atoms, got them octet, and I still have electrons left. I dump them on the central atom. Remember that in Lewis structure? Well, and those are called the lone pairs. Each lone pair counted as one electron cloud. Okay, and in that case, your carbon here, okay, has two electron clouds. And two electron clouds, we have already seen an example of that. Let's go back. So, two electron clouds, and that means linear, and that's linear geometry. And because you don't have lone pairs, remember we say the difference between the shape and geometry on our last exam is because, okay, you have lone pairs on it. And in this case, we don't have lone pairs, so linear geometry and linear shape. So carbon dioxide is a linear molecule, okay, shape and geometry. All right, so when you have two things or three things, two electron clouds or three electron clouds surrounding the central atom, it's really easy. Okay, it's either 180 degree or 120 degree. Now, what if you have four things, four electron clouds surrounding your central atom? Well, let's see. let's use a very simple example. Methane or carbon tetrahydride. Okay, so carbon, hydrogen, 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 and that's a total of the 8 electrons. 4 from carbon, 1 each from hydrogen. Okay, so this is obviously the correct Lewis structure for CH4. Now, what's the shape of the molecule? What's the geometry of the molecule? You look at the way that we draw this, you go, well, you had 180 degree, you have 120 degree, and now you have 4 things. You gotta have like a 90 degree. The answer is no. These guys don't have 90 degree. Well, what do you mean? Like, you gotta think about this. These guys now are in the space when we're discussing now geometry and the molecular shape. Okay, so what's the difference now with 4 electron clouds? Well, 4 electron clouds can actually stay a little further from each other away and still be equivalent, okay, when you construct them. And how? Well, let me show you. Here's your carbon nucleus, okay? And you would have 1 hydrogen bonded to it. Okay, so let's use this empty circle to deal with it, to represent. So this is carbon, this is hydrogen, so that's first hydrogen. The second hydrogen is going to be like this. The third hydrogen, okay, I'm going to try to use a different shape to represent that pair of electron bonding the carbon and hydrogen. Okay, and it's like that. And then I'm going to use another different line to represent the fourth hydrogen. Okay, so that now, okay, is, and try to view this as a 3D model. Okay, both of these 2 bonds are in the plane of the screen, but this one is going from outside into the screen, and this one is going from the inside towards the out of your computer screen. Okay, and now this is what we call a tetrahedral geometry. Any central atom that has 4 electron clouds on it, okay, regardless of whether these electron clouds are bonds or lone pairs, okay, will have this same tetrahedral geometry. Well, what kind of shape is this? Well, for this guy, obviously, it's also tetrahedral shape, because what changes your shape from the geometry is the lone pairs. This guy don't have any lone pairs. Okay, now what about ammonia? Drawing the Lewis structure again should be pretty quick for this, because you also have 8 electrons and bonding 3 hydrogen, and you have 1 lone pair left. And you put that on the central atom. Now, okay, so now what does this look like? You would have nitrogen in the center, one hydrogen here, another hydrogen here. Let's say the third hydrogen here, and then the fourth. Oh, I don't have a fourth hydrogen. This is it. Okay, oh, forgot one thing. The angle here, okay, is 109 degree. Okay, now, and for the tetrahedral geometry. Now, same deal for ammonia, only the difference is this time, okay, let's put that hydrogen there, make it easier to look at. Now, that electron pair is there. It belongs to nitrogen. It's extended out. It occupies one of the 4 positions of your tetrahedral structure. And you can see that from the picture I draw. And the drawing is not that good, but I think you should be able to get an idea. Okay? Now, so no question about it, with 4 electron clouds surrounding the nitrogen atom, okay, this is definitely tetrahedral geometry. Okay? But this is not a tetrahedral shape. Okay? Why? Because what does tetrahedral mean? Tetra means 4. Hedral is really coming from head. This is a 4-headed monster. Count your hydrogens. You have 4 of them. Okay, each of them is one of the heads for your structure. Do you have 4 heads here for the hydrogen? No, you only have 3 hydrogen. This is a lone pair. You can't see it. And if you can't see it, you cannot count it into your shape. And that's why this is what we call a trigonal pyramidal shape. Okay, we're going to talk about more examples, but before we finish here, I want for this lecture, I want you to see something.